Now let's look at the spectrum of the double sideband suppressed carrier AM signal. We start with the time signal. Phi double sideband, as a function of time, is equal to the message signal x of t times the amplitude of the carrier AC times cosine of 2 pi fct. We find the spectrum by taking the Fourier transform of this function. And when we take the Fourier transform, we'll get capital Phi, double sideband. It will now be a function of frequency. That's going to be the Fourier transform of the product of these two time functions, so that using the modulation theorem, what this will give us is the Fourier transform of the message signal, which is capital X of f, and that will be convolved with the Fourier transform of the cosine, which will have a scale factor AC divided by 2, and then we have delta f minus fc plus delta f plus fc. That would be a pair of delta functions. Okay, so the Fourier transform of x of t is simply capital X of f. The Fourier transform of the carrier signal has a scale factor from the amplitude of AC, and the Fourier transform of the cosine is 1/2 delta f minus fc plus 1/2 delta f plus fc. It's a pair of delta functions. So if we were to sketch the spectra of these signals, let's say the Fourier transform of the message signal has some kind of shape like this. This then would be convolved with the Fourier transform of the carrier signal, which is a pair of delta functions located at plus fc and minus fc, and it has an area AC over 2. When we carry out this convolution, we get the spectrum of the message signal is shifted up and centered at the frequency of the carrier signal. So this shifts the baseband. This is the baseband spectrum. Shifted to the carrier frequency. So when we carry out the convolution, we can graphically illustrate that by taking this shape and replicating it and centering it at the carrier frequency. So we get a shape that looks like this, and a shape, the same replicated shape here centered at minus fc, and it will have a certain scale given by the magnitude of the Fourier transform and the scale of AC over 2. But frankly, I'm not terribly interested in the scale. We could write this as AC over 2 times capital X f minus fc. That's this shape shifted to the right. And this is AC over 2 times capital X of f plus fc. The same shape shifted to the left. When we take the Fourier transform of our example message signal, the sum of these two sinusoids, we find it gives us a pair of delta functions. I took the Fourier transform using the fast Fourier transform function in MATLAB and plotted out the fast Fourier transform, and I found that it clearly gives a pair of delta functions, one located at plus and minus 4 hertz, and the second pair of delta functions located at plus and minus 6 hertz. The carrier signal is a cosine with an amplitude of 1 and a frequency of 40. We take the fast Fourier transform of the carrier signal and we get a pair of delta functions, one located at delta f minus 40 to the right and one at delta f plus 40 to the left. The Fourier transform of the double sideband suppressed carrier amplitude modulated signal leads to the spectrum of the baseband message signal being shifted and replicated and centered at the carrier frequency.